Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In 1928, Alexander Fleming returned to his cluttered laboratory at St. Mary's Hospital in London after a brief vacation. What he discovered would revolutionize medicine forever: a contaminated petri dish that would save millions of lives. The bacterial culture he had been studying was now invaded by an uninvited guest, a blue-green mold that had somehow cleared away the surrounding bacteria like an invisible force field. This wasn't just contamination, it was revelation. Fleming's accidental discovery of penicillin represents one of history's most profound examples of serendipity in science. The Scottish bacteriologist had unknowingly stumbled upon the first true antibiotic, a substance that would transform humanity's relationship with infectious disease. But what made this moment extraordinary wasn't just the discovery itself. It was Fleming's ability to recognize the significance of what others might have dismissed as a ruined experiment. The mold, later identified as Penicillium notatum, had produced a substance that actively killed nearby Staphylococcus bacteria. Fleming extracted this mystery compound and began systematic testing, eventually demonstrating its remarkable ability to combat various bacterial infections without harming human tissue. By the 1940s, mass production of penicillin was saving countless lives during World War II, earning it the nickname the Wonder Drug. This serendipitous discovery raises a fascinating question. If such revolutionary breakthroughs can happen accidentally in Earth-based laboratories, what might we discover in the vast unexplored realm of space? The cosmos presents an environment unlike anything on our planet. Extreme radiation, microgravity, temperature fluctuations from -270 degrees Celsius to over 1,000 degrees Celsius, and chemical conditions that simply don't exist terrestrially. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Space agencies worldwide are increasingly recognizing that the unique conditions of space might hold keys to medical breakthroughs we cannot achieve on Earth. The International Space Station, or ISS, has become humanity's first orbital laboratory, where researchers conduct experiments impossible under terrestrial conditions. Microgravity affects protein crystallization, cellular behavior, and even how microorganisms interact with potential therapeutic compounds. Consider the implications. If Fleming's mold could produce penicillin under Earth-specific environmental conditions, what might similar organisms produce under the radically different conditions of space? The absence of gravity, exposure to cosmic radiation, and the vacuum of space create selective pressures that could drive biological systems toward entirely new chemical innovations. Recent research aboard the ISS has already demonstrated that proteins crystallize differently in microgravity, often forming larger, more perfect structures than their Earthbound counterparts. These superior crystals provide clearer insights into protein function and could lead to more effective drug designs. If fundamental biological processes behave differently in space, the therapeutic potential of space-based research becomes enormous. The search for new antibiotics has become increasingly urgent as antibiotic-resistant bacteria continue to evolve. Traditional drug discovery methods are struggling to keep pace with bacterial adaptation, creating what many scientists call an antibiotic crisis. Perhaps the solution lies not in Earth's laboratories, but in the infinite laboratory of space itself. Fleming's contaminated petri dish teaches us that breakthrough discoveries often come from unexpected places. As we stand on the threshold of a new era in space exploration, we must ask ourselves, could the next revolutionary antibiotic be waiting among the stars in conditions so alien to Earth that we haven't even imagined the possibilities? The cosmos may hold medical treasures that could save humanity from its microscopic adversaries. The golden age of antibiotics is under siege. Across hospital corridors worldwide, a microscopic war rages between humanity's chemical arsenal and increasingly cunning bacterial adversaries. What began as humanity's triumph over infectious disease has evolved into a complex arms race, one that bacteria are beginning to win through the relentless process of evolutionary adaptation. Antibiotic resistance represents one of the most pressing threats to modern medicine. The World Health Organization has classified it as one of the top 10 global public health threats facing humanity. Each year, antibiotic-resistant infections kill approximately 700,000 people globally, a number projected to reach 10 million annually by 2050 if current trends continue unchecked. The mechanism behind this crisis is elegantly simple, yet devastatingly effective. When antibiotics are used, they kill susceptible bacteria while inadvertently selecting for resistant variants. These surviving bacteria multiply rapidly, passing their resistance genes to offspring and sometimes even to entirely different bacterial species through horizontal gene transfer. This process creates superbugs, pathogens that resist multiple antibiotics simultaneously, leaving physicians with increasingly limited treatment options. Methicillin-resistant Staphylococcus aureus, commonly known as MRSA, exemplifies this challenge. Once easily treatable with penicillin, this bacterium has developed resistance to multiple antibiotic classes, making infections potentially life-threatening. Similar patterns have emerged with tuberculosis, gonorrhea, and numerous other bacterial diseases that were once considered conquered. The pharmaceutical industry's response has been disappointingly inadequate. Since 1970, only 4 new classes of antibiotics have been discovered and brought to market. The last major breakthrough occurred in 1987 with the development of lipopeptide antibiotics. This 4-decade drought in antibiotic innovation reflects both the inherent difficulty of drug discovery and economic realities that make antibiotic development less profitable than treatments for chronic conditions. Traditional antibiotic discovery relies heavily on screening natural compounds produced by soil microorganisms. However, this approach faces fundamental limitations. After decades of intensive screening, researchers have likely identified most easily accessible antibiotic-producing organisms in terrestrial environments. The low-hanging fruit of antibiotic discovery has been largely harvested, forcing scientists to explore increasingly exotic sources and complex synthetic approaches. Synthetic chemistry offers alternative pathways, but designing effective antibiotics from scratch remains extremely challenging. Successful antibiotics must penetrate bacterial cell walls, reach their molecular targets, avoid bacterial resistance mechanisms, and remain non-toxic to human cells, all while maintaining chemical stability. This multidimensional optimization problem has proven remarkably difficult to solve through conventional drug design approaches. The economic dynamics of antibiotic development compound these scientific challenges. Unlike treatments for chronic diseases that patients take continuously, antibiotics are used for short periods and ideally reserved for serious infections to prevent resistance development. This usage pattern makes antibiotic development less financially attractive, leading many pharmaceutical companies to abandon antibiotic research programs despite the obvious medical need. Current research strategies focus on modifying existing antibiotics, developing combination therapies, and exploring alternative approaches like bacteriophage therapy and immunomodulation. While these efforts show promise, they primarily represent incremental improvements rather than revolutionary breakthroughs comparable to Fleming's original discovery. The scientific community increasingly recognizes that transformative advances may require fundamentally different approaches. Some researchers explore deep-sea organisms, others investigate symbiotic relationships in extreme environments, and still others examine the chemical warfare occurring within microbial communities. Each approach seeks to identify novel biological contexts that might produce unprecedented therapeutic compounds. This desperation for new sources of antibiotic compounds has led scientists to consider increasingly exotic environments. If terrestrial microorganisms have been exhaustively studied, perhaps the answer lies beyond Earth itself. The cosmos presents biological pressures and environmental conditions so radically different from anything terrestrial that they might drive the evolution of entirely new classes of antimicrobial compounds. The antibiotic crisis demands innovative thinking and willingness to explore uncharted territories. As Fleming discovered nearly a century ago, breakthrough solutions often emerge from unexpected sources. Perhaps our next great medical revolution awaits not in Earth's soil but among the stars themselves. The universe operates as an enormous laboratory, conducting experiments under conditions so extreme they would instantly destroy most terrestrial life. Yet life, as we've learned from studying extremophiles on Earth, possesses an almost incomprehensible ability to adapt, survive, and even thrive in environments once thought completely hostile to biological processes. Space presents biological challenges unlike anything encountered on Earth. The vacuum of space creates pressure differentials that would cause most cells to rupture instantly. Cosmic radiation bombards any exposed organism with high-energy particles that shatter molecular bonds and damage genetic material. Temperatures fluctuate wildly, ranging from near absolute zero in shadowed regions to over 1,000 degrees Celsius in direct sunlight. Despite these harsh conditions, astrobiologists increasingly believe that life might exist in various cosmic environments. The concept of panspermia suggests that microorganisms could potentially survive interplanetary travel, protected within meteoroids or cometary material. If life can endure such journeys, it might also adapt to the intermediate environments it encounters along the way. Earth's extremophiles provide compelling evidence for life's adaptability. Deinococcus radiodurans, nicknamed Conan the bacterium, can survive radiation doses 3,000 times higher than what would kill humans. This remarkable organism repairs its severely damaged DNA using sophisticated molecular machinery, essentially resurrecting itself from near-complete genetic destruction. Such capabilities suggest that similar organisms might survive and even adapt to space's radioactive environment. Tardigrades, microscopic animals, also known as water bears, represent perhaps the most space-hardy life forms discovered on Earth. These remarkable creatures can survive complete dehydration, temperatures approaching absolute zero, pressure 6 times greater than the deepest ocean trenches, and radiation levels hundreds of times higher than lethal doses for humans. Most remarkably, tardigrades have actually survived exposure to open space during orbital experiments, demonstrating that complex multicellular life can endure cosmic conditions. The selective pressures operating in space would drive biological adaptation in directions completely different from terrestrial evolution. Organisms surviving in space would need sophisticated DNA repair mechanisms, enhanced radiation resistance, and cellular structures capable of functioning without atmospheric pressure. These extreme adaptations might produce biochemical innovations unavailable through terrestrial evolutionary pathways. Microgravity itself creates unique biological opportunities. Without gravitational constraints, cellular processes and molecular interactions occur differently than on Earth. Protein folding, membrane dynamics, and metabolic pathways all function under altered physical conditions. These changes might drive the evolution of novel biochemical compounds, including potentially revolutionary antimicrobial substances. The ISS has provided preliminary insights into how microgravity affects biological systems. Bacteria grown in space exhibit altered antibiotic resistance patterns, sometimes becoming more susceptible to certain drugs while developing resistance to others. These observations suggest that space conditions could influence how microorganisms produce and respond to antimicrobial compounds. Cosmic chemistry operates under fundamentally different rules than terrestrial chemistry. The interstellar medium contains molecules that exist only under extreme conditions, exotic compounds that might serve as building blocks for entirely new classes of therapeutic agents. Polycyclic aromatic hydrocarbons, complex carbon chains, and even amino acids have been detected in space, suggesting that the chemical diversity of the cosmos far exceeds what we find on Earth. Recent discoveries of organic compounds on Mars, methane plumes on Enceladus, and complex chemistry in Titan's atmosphere demonstrate that space environments can support sophisticated chemical processes. These findings expand our understanding of where life might exist and what forms it might take under non-terrestrial conditions. The concept of astrobiology has evolved from speculative science fiction to rigorous scientific discipline. Researchers now seriously consider how life might adapt to environments on Mars, Europa, Enceladus, and even in the upper atmospheres of gas giants. Each environment presents unique challenges that would drive different evolutionary solutions. If life exists in these exotic environments, it has likely evolved biochemical strategies for surviving conditions that would instantly kill terrestrial organisms. These survival mechanisms might include novel antimicrobial compounds designed to function under extreme conditions, compounds that could revolutionize medicine if we could discover and adapt them for terrestrial use. The cosmos represents the ultimate extreme environment laboratory, conducting evolutionary experiments across billions of years under conditions impossible to replicate on Earth. Understanding how life might adapt to these conditions could unlock biochemical innovations that terrestrial evolution never explored. The absence of gravity creates one of the most profound experimental conditions available to human science. Aboard the International Space Station, researchers have discovered that removing Earth's constant gravitational influence fundamentally alters how biological systems function, opening unprecedented opportunities for medical research and drug discovery. Microgravity affects cellular behavior in ways that continue to surprise scientists. Without gravitational orientation cues, cells organize themselves differently, form alternative structures, and exhibit metabolic patterns distinct from their terrestrial counterparts. These changes aren't merely interesting curiosities, they represent potential pathways to medical breakthroughs impossible to achieve under Earth's gravitational constraints. Protein crystallization provides the most dramatic example of microgravity's research potential. Proteins are complex molecular machines whose three-dimensional structures determine their biological functions. Understanding these structures is crucial for designing effective drugs, but growing high-quality protein crystals on Earth faces significant challenges due to gravitational effects. On Earth, gravity causes density variations and convection currents during crystal formation, creating imperfections and limiting crystal size. These flaws make it difficult to determine precise protein structures using X-ray crystallography. In microgravity, these disturbances disappear, allowing proteins to form larger, more perfect crystals with fewer defects. The results have been remarkable. Protein crystals grown aboard the ISS are often 10 to 100 times larger than their Earth-grown counterparts, with significantly improved internal organization. These superior crystals provide clearer, more detailed structural information. That enables more precise drug design. Several pharmaceutical companies now regularly conduct protein crystallization experiments in space as part of their drug development processes. Lysozyme, an enzyme found in tears and saliva that naturally fights bacterial infections, exemplifies this potential. Space-grown lysozyme crystals revealed structural details invisible in Earth-based studies, leading to better understanding of how this natural antibiotic functions. Such insights could guide the development of more effective synthetic antimicrobial compounds based on lysozyme's molecular architecture. Bacterial behavior also changes dramatically in microgravity. Studies aboard the ISS have shown that bacteria exhibit altered growth patterns, modified biofilm formation, and different responses to antibiotics when grown in space. Some bacteria become more virulent, while others show increased susceptibility to certain antimicrobial treatments. Salmonella typhimurium, a pathogen that causes food poisoning, becomes significantly more dangerous in microgravity. However, this increased virulence comes with trade-offs. Space-grown salmonella also shows altered metabolic pathways that might reveal new therapeutic targets. Understanding these microgravity-induced changes could lead to novel treatment strategies for bacterial infections. Conversely, some beneficial bacteria exhibit enhanced production of useful compounds in microgravity. Streptomyces species, which produce many of our current antibiotics, show modified secondary metabolite production patterns in space. These alterations might lead to the discovery of new antibiotic compounds or improved production methods for existing drugs. The pharmaceutical industry has begun investing heavily in space-based research. Companies like Merck, Bristol-Myers Squibb, and Eli Lilly have conducted experiments aboard the ISS, focusing on protein crystallization and cellular behavior studies. Their results consistently demonstrate that microgravity conditions can provide insights unavailable through terrestrial research. Tissue engineering represents another promising application of microgravity research. Without gravitational constraints, cells can organize into three-dimensional structures more similar to natural tissues. These space-grown tissue models provide better platforms for testing potential drugs and understanding disease mechanisms. The unique environment of space also affects how drugs themselves behave. Pharmaceutical formulations that might be unstable on Earth could remain viable in microgravity, opening possibilities for new drug delivery systems and therapeutic approaches. The absence of sedimentation and reduced convection in microgravity create conditions ideal for studying drug interactions and developing novel formulations. Commercial space stations planned for the coming decades will dramatically expand research opportunities. These facilities will provide dedicated laboratory space, longer experiment durations, and improved research capabilities compared to current ISS operations. The prospect of conducting months-long experiments in carefully controlled microgravity conditions could accelerate drug discovery timelines significantly. Microgravity research has already contributed to several drug development programs currently in clinical trials. While these early successes focus primarily on cancer and autoimmune diseases, the principles apply equally to antibiotic discovery. The structural insights gained from space-based protein studies could guide the development of more effective antimicrobial drugs. The potential of microgravity-based research extends beyond immediate practical applications. By understanding how biological systems function differently in space, scientists gain fundamental insights into life's mechanisms that could inspire entirely new approaches to medicine and drug discovery. The cosmos operates as a vast chemical laboratory, synthesizing molecules under conditions so extreme and diverse that they stretch our understanding of what chemistry can accomplish. From the frozen surfaces of distant moons to the superheated atmospheres of exoplanets, space environments create opportunities for biochemical innovations that terrestrial life has never explored. Interstellar space contains a surprising diversity of organic compounds. Radio telescopes have detected over 200 different molecules in the interstellar medium, including complex carbon-based compounds like polycyclic aromatic hydrocarbons, amino acids, and even simple sugars. These discoveries demonstrate that the building blocks of life form naturally throughout the universe under conditions radically different from those on Earth. The Murchison meteorite, which fell in Australia in 1969, contained over 90 different amino acids, far more diversity than the 20 amino acids used by terrestrial life. This extraterrestrial chemistry suggests that life elsewhere might utilize completely different biochemical foundations, potentially producing antimicrobial compounds based on molecular architectures unknown to Earth-based organisms. Titan, Saturn's largest moon, presents a particularly intriguing example of alien chemistry. Its thick atmosphere contains methane, ethane, and complex hydrocarbons that rain down onto the surface, creating rivers and lakes of liquid methane. This hydrocarbon-based chemistry operates at temperatures of -179 degrees Celsius, where water exists only as rock-hard ice. If life exists on Titan, it would necessarily employ completely different biochemistry than terrestrial organisms. Instead of water-based cellular processes, Titanian life might use liquid methane or ethane as a solvent. Such organisms would produce entirely different classes of biomolecules, potentially including antimicrobial compounds based on hydrocarbon chemistry rather than the protein and peptide-based antibiotics familiar on Earth. Europa and Enceladus, moons of Jupiter and Saturn respectively, harbor subsurface oceans beneath their icy shells. These oceans contain more water than all of Earth's oceans combined, maintained in liquid form by tidal heating from their parent planets. The chemistry of these hidden seas remains largely mysterious, but they likely contain dissolved minerals and organic compounds in concentrations and combinations never found on Earth. Life in these subsurface oceans would face unique challenges. Perpetual darkness, high pressure and chemical environments dominated by sulfur, and other compounds toxic to most terrestrial life. Organisms adapted to such conditions might produce antimicrobial compounds designed to function in high-pressure, chemically exotic environments, compounds that could prove remarkably effective against Earth-based pathogens. The search for extremophiles on Earth provides insights into possible alien biochemistries. Organisms living near deep-sea hydrothermal vents utilize chemosynthesis rather than photosynthesis, deriving energy from chemical reactions involving hydrogen sulfide and other compounds that would poison most life forms. These organisms produce unique enzymes and protective compounds that allow them to thrive in environments that mimic conditions found throughout the solar system. Pyrococcus furiosus thrives at temperatures exceeding 100 degrees Celsius, using proteins stabilized by unique molecular adaptations. These thermostable proteins maintain their function under conditions that would denature most biological molecules. Similar adaptations might exist in hypothetical life forms on Venus or in the atmospheres of gas giants, producing antimicrobial compounds stable at extreme temperatures. Halophilic archaea survive in salt concentrations that would kill other organisms by using specialized cellular machinery and protective compounds. Life on Mars, if it exists, might face similar osmotic challenges from perchlorate-rich soils, potentially evolving analogous protective mechanisms that could inspire new therapeutic approaches for treating drug-resistant infections. The concept of biochemical diversity extends beyond individual organisms to entire ecosystems. Alien worlds might support communities of organisms with biochemistries based on silicon rather than carbon, sulfur metabolism instead of oxygen, or entirely different genetic coding systems. Each alternative biochemistry could produce antimicrobial compounds based on molecular principles unknown to terrestrial science. Recent discoveries of phosphine in Venus's atmosphere and methane on Mars hint at active chemistry that might support life. While these detections remain controversial, they suggest that biochemical processes could operate under planetary conditions previously considered sterile. If life can exist in such environments, it has likely evolved chemical defense mechanisms unlike anything found on Earth. Synthetic biology increasingly explores alternative biochemistries by engineering organisms with expanded genetic codes or novel metabolic pathways. These efforts provide previews of what truly alien biochemistry might accomplish. Organisms engineered with unnatural amino acids or alternative genetic codes produce proteins with properties impossible in natural terrestrial life, including enhanced stability and novel antimicrobial activities. The Drake equation suggests that numerous technological civilizations might exist throughout the galaxy. If alien species have developed biotechnology, they might have discovered antimicrobial compounds far more advanced than our current antibiotics. While we cannot yet access such knowledge directly, understanding the principles of alien biochemistry could guide us towards similar innovations through independent discovery. The vast chemical diversity of the cosmos represents an untapped resource for pharmaceutical innovation. By studying extremophile adaptations, analyzing extraterrestrial organic compounds, and considering alternative biochemistries, researchers might identify entirely new approaches to combating antibiotic-resistant pathogens. The transformation of space from a realm of pure exploration to a platform for commercial manufacturing represents one of the most significant developments in modern pharmaceutical research. Major pharmaceutical companies, space agencies, and private ventures are increasingly recognizing that the unique conditions of space offer unprecedented opportunities for drug discovery and production that could revolutionize terrestrial medicine. NASA's National Laboratory aboard the International Space Station has become the focal point for space-based pharmaceutical research. Since 2011, this orbital facility has hosted hundreds of experiments investigating how microgravity affects cellular behavior, protein structure and drug effectiveness. The results consistently demonstrate that space-based research can provide insights and capabilities unavailable through traditional terrestrial methods. Merck's collaboration with the ISS National Laboratory exemplifies the pharmaceutical industry's growing interest in space-based research. The company has conducted multiple experiments investigating how microgravity affects protein crystallization, particularly focusing on Keytruda, their breakthrough cancer immunotherapy drug. The superior protein crystals grown in space have provided detailed structural information that enables more precise drug design and potentially more effective therapeutic formulations. Bristol Myers Squibb has similarly invested in space-based research through their collaboration with the Center for the Advancement of Science in Space. Their experiments focus on understanding how microgravity affects immune system function and cancer cell behavior. These studies have revealed that certain cancer cells become more susceptible to treatment in microgravity, opening possibilities for developing more effective therapeutic protocols. The commercial space industry has recognized the enormous potential of pharmaceutical manufacturing in space. Companies like Axiom Space, Varda Space Industries, and Space Tango are developing specialized platforms designed specifically for space-based manufacturing and research. These ventures promise to make space-based pharmaceutical research more accessible and cost-effective than current ISS-based programs. Microgravity manufacturing offers several distinct advantages for pharmaceutical production. The absence of gravitational settling allows for more uniform mixing of compounds, while reduced convection enables more controlled chemical reactions. These conditions are particularly beneficial for producing complex biological drugs, like monoclonal antibodies and gene therapies, which require precise molecular assembly. Protein crystallization remains the most successful application of space-based pharmaceutical research. Companies have consistently achieved superior results when growing protein crystals in microgravity, leading to better understanding of drug targets and more effective therapeutic designs. The Japanese company SpaceBD has established a dedicated protein crystal growth facility aboard the ISS, providing commercial crystallization services to pharmaceutical companies worldwide. Tissue engineering represents another promising application of space-based manufacturing. The microgravity environment allows cells to organize into three-dimensional structures more similar to natural tissues than possible in terrestrial laboratories. These space-grown tissue models provide superior platforms for testing potential drugs and understanding disease mechanisms, potentially accelerating drug discovery timelines. Eli Lilly has conducted groundbreaking research on crystallizing their diabetes drug aboard the ISS. The microgravity-grown crystals exhibited improved uniformity and stability compared to Earth-produced versions, potentially leading to more effective drug formulations with longer shelf lives and improved bioavailability. The economics of space-based pharmaceutical manufacturing are becoming increasingly favorable. While launching materials to space remains expensive, the high value of pharmaceutical products makes space manufacturing economically viable for certain applications. A single successful drug discovery enabled by space-based research could generate billions of dollars in revenue, easily justifying substantial space-based research investments. Private space stations planned for the late 2020s and early 2030s will dramatically expand pharmaceutical research opportunities. These facilities will offer dedicated laboratory space, longer experiment durations, and improved research capabilities compared to current ISS operations. Companies like Axiom Space are designing their stations specifically to accommodate pharmaceutical research and manufacturing. Automated manufacturing systems developed for space applications could revolutionize pharmaceutical production. The precision and control required for space-based manufacturing push technological boundaries, leading to innovations that improve terrestrial production processes as well. These advances could reduce manufacturing costs and improve drug quality across the entire pharmaceutical industry. The regulatory framework for space-based pharmaceutical manufacturing is still evolving. The Food and Drug Administration and European Medicines Agency are developing guidelines for approving drugs produced or tested in space. These regulatory pathways will need to address unique aspects of space-based research while maintaining safety and efficacy standards. Several pharmaceutical companies are investigating how space-based research could accelerate antibiotic discovery. Specifically, the unique bacterial behaviors observed in microgravity, combined with superior protein crystallization capabilities, could lead to more effective approaches for combating antibiotic-resistant pathogens. International collaboration in space-based pharmaceutical research continues to expand. The European Space Agency, Japanese Aerospace Exploration Agency, and other national space programs are establishing partnerships with pharmaceutical companies to conduct joint research aboard the ISS and future commercial space stations. The success of current space-based pharmaceutical research has created momentum for even more ambitious projects. Proposed deep space manufacturing facilities could take advantage of the unique conditions found at Lagrange points, where gravitational forces from Earth and the Moon balance each other, creating extremely stable environments ideal for sensitive manufacturing processes. The convergence of space exploration and medical research stands poised to usher in an unprecedented era of pharmaceutical innovation. As humanity prepares for deep space exploration and eventual colonization of other worlds, the development of space-based medicine becomes not just an opportunity, but an absolute necessity for our species' survival beyond Earth. NASA's Artemis program, designed to establish a permanent human presence on the Moon by the late 2020s, will create humanity's first extraterrestrial medical research facility. The lunar environment offers unique advantages for pharmaceutical research: lower gravity than Earth, but higher than the ISS, protection from some cosmic radiation while still maintaining exposure to space conditions, and the possibility of conducting long-term experiments without the logistical constraints of orbital facilities. The Artemis Lunar Gateway, a planned space station orbiting the Moon, will serve as both a staging area for lunar missions and a dedicated research platform. This facility will enable months-long pharmaceutical experiments in deep space conditions, potentially revealing how extended exposure to cosmic radiation and reduced gravity affects biological systems and drug effectiveness. Mars presents even more intriguing possibilities for medical research. The red planet's environment, with its thin atmosphere, extreme temperature variations and high radiation levels, could drive the evolution of extremophile organisms that produce entirely novel antimicrobial compounds. Future Mars missions will include extensive astrobiology components specifically designed to search for life and analyze any discovered organisms for their pharmaceutical potential. The James Webb Space Telescope continues to revolutionize our understanding of cosmic chemistry by detecting complex organic molecules in the atmospheres of exoplanets and in interstellar space. These observations provide blueprints for alternative biochemistries that could inspire new approaches to drug design. As we discover more chemically diverse worlds, we expand our library of potential molecular architectures for pharmaceutical innovation. Europa Clipper, scheduled to launch in 2024, will conduct detailed studies of Jupiter's ice-covered moon and its subsurface ocean. The mission's sophisticated instruments will analyze the moon's chemistry and search for signs of life in an environment completely unlike Earth. Any life discovered in Europa's hidden seas would represent a completely independent evolution of biochemistry, potentially producing antimicrobial compounds based on molecular principles unknown to terrestrial science. Private space companies are accelerating the timeline for space-based pharmaceutical manufacturing. SpaceX's Starship promises to dramatically reduce the cost of transporting materials and equipment to space, making large-scale pharmaceutical manufacturing facilities economically viable. Blue Origin's planned orbital platforms will provide dedicated space for pharmaceutical research and production, independent of government facilities. The development of closed-loop life support systems for long-duration space missions will require unprecedented understanding of how pharmaceuticals behave in isolated environments. This research will necessarily advance our knowledge of drug stability, effectiveness, and safety, under conditions that could translate to improved terrestrial medical treatments. Synthetic biology platforms deployed in space could enable the production of pharmaceuticals using local resources rather than materials transported from Earth. Engineered microorganisms could potentially use Martian atmospheric carbon dioxide or lunar regolith minerals to produce essential medicines, making long-term space colonization medically sustainable. The timeline for space-based antibiotic discovery appears increasingly promising. Current ICES experiments have already identified several promising leads, including modified bacterial behaviors and novel protein structures that could guide new drug development. Commercial space stations coming online in the late 2020s will accelerate this research significantly. By the 2030s, space-based pharmaceutical manufacturing could become routine for certain high-value drugs. The combination of superior microgravity conditions, automated manufacturing systems, and reduced launch costs could make space production economically competitive with terrestrial manufacturing for specialized pharmaceuticals. The search for extraterrestrial life, whether microbial or complex, could yield revolutionary medical discoveries. Even discovering simple microorganisms adapted to alien environments would provide insights into alternative biochemical strategies that could inspire new therapeutic approaches. The potential discovery of complex alien biochemistry would represent perhaps the greatest pharmaceutical opportunity in human history. Artificial intelligence systems aboard future space missions will enable real-time analysis of discovered organisms and their potential pharmaceutical applications. These AI-powered laboratories could conduct initial screening and optimization of promising compounds automatically, dramatically accelerating the drug discovery process. The implications extend far beyond antibiotics. Space-based research could lead to breakthroughs in cancer treatment, neurological disorders, genetic diseases, and aging-related conditions. The unique environment of space provides research opportunities that could address virtually every major medical challenge facing humanity. International cooperation in space-based medical research continues to expand, with proposals for collaborative pharmaceutical research stations managed jointly by multiple nations. These partnerships could pool resources and expertise to tackle medical challenges that no single country could address alone. The ultimate vision encompasses a future where space-based medical research not only solves Earth's antibiotic crisis, but enables human expansion throughout the solar system. As we venture to Mars, the outer planets, and eventually to other star systems, the medicines we discover in space may prove essential for our survival as an interplanetary species. Fleming's accidental discovery of penicillin in 1928 saved millions of lives and demonstrated the power of serendipitous scientific observation. Today, as we extend our reach into the cosmos, we carry with us the same spirit of discovery and the same openness to unexpected breakthroughs. The universe awaits, vast and full of possibilities, ready to reveal its secrets to those brave enough to seek them among the stars.